Hi everybody. This very first calculus lesson is about gaining an understanding of instantaneous velocity, a central question that motivated the creation of the calculus itself. Let us begin with an animation depicting balls of very different weights being dropped at the same instant from the beautiful Leaning Tower in Pisa, Italy, much as Galileo is said to have done around the beginning of the 17th century. Galileo observed that balls fell to the ground at the same time, contrary to what Aristotle had taught in ancient times. In what Galileo considered one of his greatest achievements, he, for the first time in history, defined a quantitative notion of speed and velocity. In particular, he defined constant and then later average velocity of an object traveling along a straight line path. He discovered that the distance the balls travel in time t varies with the square of the time traveled, that is, proportional to t squared. Since the size of the ball does not matter, we shall, in our mathematical model of the ball's motion, replace the ball with a simple moving point, moving straight downward, as we see in the animation. We now move to the mathematics of Galileo's discovery.
Hi, this is Frank, and I will continue this lesson on average and instantaneous velocity with the following example. Assume a ball is dropped from a height of 50 meters, subject only to the gravitational pull of the Earth, which in particular means that we assume that there's no air resistance. The position or height of the ball above the ground at time t is given by the formula s of t equal to 50 minus 4.9 t squared, where t is measured in seconds and s of t in meters. This is in fact an accurate representation of how a ball would fall. This goes back to Galileo in the 17th century. Now, in this graphic, you can see a rendering of the situation that we might be in. Here we have the Leaning Tower of Pisa, which in reality is approximately 50 meters from the ground to its observation level. We're dropping a ball, and as time increases, the ball is dropping towards the ground. The function s of t then tells us exactly how high above the ground is at time t. So this 48.775 meters then is really nothing other than s of 0.5. That's the meaning of this formula. And in general, at some time t sub 0, s of t sub 0 represents the height of the ball above the ground. Now, what are we actually trying to calculate? I haven't told you yet. Here we go. We will try to calculate the average velocity of the ball between t equal to 2 seconds and t equal to 3 seconds. Now, how are we going to do that? Well, let us review the definition of average velocity. This also goes back to Galileo. Assume an object is moving on a straight line path and its position at time t, subject to some fixed reference frame, such as the ground in our example above, is given by s of t. The average velocity, and we're naming it delta s over delta t, of the object on the time interval from t1 to t2 is defined as, here's what we're defining, delta s over delta t, equal to, and here comes what we're using to define it, namely the quotient s of t2 minus s of t1 divided by t2 minus t1. The numerator here represents the change in position of the object, and the denominator the corresponding change in time. Now, this formula may seem relatively easy for us to understand and use, but it was not easy to discover, and it really needed the genius of somebody like Galileo for that to occur. Now, let's use it in our situation. We need to essentially calculate delta s over delta t, and therefore we need to know what is s of t and what is t2 and what is t1. S of t is 50 minus 4.9 t squared. So let's write that down so that we can then figure out what we need to calculate. So s of t is equal to 50 minus 4.9 t squared. T2 was 3 seconds and T1 was 2 seconds. And we're asked to calculate the following expression, delta S over delta T, for this interval T1 to T2. So we need to calculate S of 3 minus S of 2 over 3 minus 2. To aid us in the calculations, I will import a table of values for S of t. So this table has two columns. In the first column, t in seconds, and in the second column, the values of the function S of t in meters. So at the time 0, the ball has not left our hand yet, and it's still at 50 meters above the ground. As time increases, it's dropping, and the height above the ground gets closer and closer to 0. And we just need to evaluate S of 3 by writing 5.9, and S of 2, 30.4, over, well, 3 minus 2, that's 1. And then we do the calculation, and we end up with minus 24.5. Now let me introduce the units. The numerator is a difference of quantities measured in meters, so this is going to be meters. And the denominator is a difference of quantities measured in seconds, so we end up with meters per second. So this is our answer. The average velocity of the ball on the time interval from 2 to 3 seconds is minus 24.5 meters per second. Now, what does this number represent? Well, the minus indicates that the ball is dropping. The 24.5 is the rate at which it is dropping on average on that time interval from t equal to 2 to t equal to 3 seconds. So on average, the ball is dropping at a rate of 24.5 meters per second in that 1 second time interval. Now, we have to note that in the formula for average velocity above, since we wrote t1, t2 as an interval, we implicitly assumed that t2 is greater than t1. In fact, if we allowed, for instance, t2 equal to t1, then we would also get S of t2 equal to S of t1 and would end up with the meaningless expression 0 over 0. In principle, this shows the challenge when trying to calculate the actual velocity of an object, such as our ball, at a given instant of time, say at t equal to 2 seconds. In part B of our example, we will investigate how to define the actual velocity of an object at a given instant of time, or what soon will be called the instantaneous velocity. Let's go to B. Determine, if possible, the instantaneous velocity of the ball at t equal to 2 seconds. Now, as we said before, we cannot directly use the formula for average velocity to compute this. On the other hand, it should be intuitively clear that our answer from part A will provide us with a rough estimate for the actual velocity of the ball at time t equal to 2 seconds. The question now is, how can we improve this estimate? The intuitive answer is to make the time interval delta t smaller. Or in other words, we will investigate the average velocity of the ball, delta s over delta t, on the time interval 2, 2 plus delta t as delta t gets closer to 0 or approaches 0. To do so, we will use the following table of values. This table has 3 columns. In the first column, we have delta t as it varies from 1 down to 0.00001, a very small number indeed. Then in the second column, we have the corresponding time interval from 2 to 2 plus delta t. And in the third column, we have the corresponding average velocity delta s over delta t. And in this example, that is always measured in meters per second. Now, in the first row of data, we actually have simply a replica of the work in part A. Delta t there was 1 second. The corresponding interval was from 2 to 3 seconds. and we calculated the average velocity to be minus 24.5 meters per second on that interval. Now, let's pick another row. Let's say delta t equal to 0.3. The corresponding time interval then is from 2 to 2.3 seconds, and the average velocity on that interval is minus 21.07 meters per second. Let's pick 0.05. Well, the average velocity there is minus 19.845. Now, let's investigate what happens to delta S over delta t as delta t is getting closer and closer to 0. Those numbers are still changing, but it may appear that delta S over delta t approaches a number close to, or for some of you, even equal to, minus 19.6 meters per second. But the problem is, how can we be sure? We have only looked at finitely many instances of delta t, and there are, well, infinitely many. If you look closely at the last 4 rows, we obtained the next one simply by dividing the previous one by 10. And there's nothing that will stop us from doing this forever. The next row will have 0.000001, and then 0.000001, and so on. These numbers may continue to change, and even if they're not, we don't know if they're not going to change again in the future. That is the problem at hand. We have an infinite process, but only finitely much information about what we're investigating. Now, when it comes to dealing with the infinite or infinite processes, the animation on Zeno's paradox in the introductory lectures has shown us how complicated this can be and how even very smart people can be led astray quite easily. So what we really need is a clear mathematical definition for this process. For it also should be clear that this process is at the core of what we need to define the instantaneous velocity. That's it for this video. Thank you for watching, and see you next time.